Since we have learned the dispersion relationship of the TE-guided mole, let's see how to find out the waveguide moles by plotting these curves. First, for TE symmetry mode and TE anti-symmetry mode, we have known that their corresponding dispersion equation is U tangent U is V and U cotangent U is minus V. For TE symmetry modes, due to this is a tangent function, you can plot the solid blue line as shown here. And for TE anti-symmetry mode, due to this is cotangent function, you can plot the red dashed lines here. Okay, after we have obtained this dispersion curve for the TE modes, the U and the V, they also have to satisfy the condition that for a given normalized frequency, for a given normalized frequency capital V, which is defined as kn2d divided by 2 times square root of 2 delta. And we know that for this condition, at this condition, the guided mode should satisfy that U square plus V square is the square of capital V. Okay, and for this figure, you see that along this axis is U, along this axis is V. So for this equation, it will correspond to the quarter circle shown here. Okay, so as you have plotted this quarter circle according to the condition of the normalized frequency, you will have several intersections with these mole curves. Then you will obtain solutions from this intersection. Okay, according to the dispersion relationship, you have plotted the mole curve for M1 mole, M0 mole, M1 mole, M2 mole. And for the operation condition, you have obtained the normalized frequency and plot the corresponding circle for the normalized frequency. And this curve will have intersection. So this intersection represents that they both satisfy the normalized frequency condition, and they are also satisfy the mole curves here. Okay, so from these intersections, you can find out their corresponding position. That is, you will find out their U and the V value. So each point they have their own U value and the V value. So for each intersection, you will find out a set of U value and the V value. Besides, we know that U is defined as HD over 2 and the V is defined as QD over 2. Since you have obtained the value of U and the V, this means that you will also have the value for H and the Q. And then we know that H is square root of N2 square K square minus beta square, and Q is beta square minus n1 square k square. So after you have obtained the value for h and q, you will then have the value of beta, which is the z component of the k vector, and this is the propagation constant for a optical waveguide MOS. Okay, and this is the process you can find out the value of beta for optical waveguide MOS. By plotting this curve, find out the intersections, and from the position you can obtain the value of beta. And from this figure, you can also see many important properties for the optical waveguide MOS. First, as you can see, if we increase the value of the normalized frequency, this means that the radius of this quarter circle will be increased. As we increase the value of the normalized frequency, the circle will become large, and then we will have more intersections with these curves, right? For example, if I reduce the radius of the circle like this, then you will have only 2 intersections. As we increase the radius, you have more intersections. So you can know that as we increase the normalized frequency, we will have more waveguide MOS. How to increase the normalized frequency? According to the expression of the normalized frequency shown here, you know that if you reduce the wavelength lambda, or if you increase the cone size, or if you increase the index difference, by these 3 ways, you can increase the value of the normalized frequency to have more waveguide MOS. Okay. The second property we can learn from this figure is the cutoff frequency of each mole. As you can see, from these 2 dispersion relationship, you can obtain the mole curves for M0 mole, M1 mole, M2 mole, and M3 moles. These moles have intersection with the U-axis. Along the U-axis, the V value is 0. So take V is 0 into these 2 equations. You can find out the value of each point here. For M0 mole, the point is 0. For M1 mole, this point is half pi. For M2 mole, this point is 2 pi over 2. For M3 mole, this point is 3 pi over 2. And you can see that if the normalized frequency is smaller than half pi, which means that you have only one intersection with the M0 mole curves. So you will have only one mole. As the normalized frequency is larger, is half pi, you will start to have intersection with the M1 mole curves. So the M1 mole will appear on this waveguide as the normalized frequency is larger than half pi. So the half pi here represent the cutoff normalized frequency for M1 mole. As for M2 mole, the corresponding cutoff normalized frequency is pi, and for M3 mole, the cutoff normalized frequency is 3 pi over 2. So these curves, this figure can tell us the cutoff normalized frequency for each mole. And from this result, you can see that the cutoff normalized of each mole increase with the mole order. Okay, as we increase the mole order, their corresponding cutoff frequency will also be increased. And then we want to know that when we will have single mode. Again, we have said that for single mode operation, which means that we only have M0 mode and we don't have M1 mode. So before M1 mode appear on this waveguide, we will have single mode operation. So the single mode operation means that the normalized frequency is smaller than the cutoff frequency of the M1 mode, which is pi over 2. And if you remember, I have told you that to keep the normalized frequency smaller than half pi for the single mode operation, we can increase the wavelength, or we can decrease the cone size, or we can reduce the index difference between core and the cladding. These are the properties we can learn from this figure, which shows you the mode curves of the guiding mode on optical waveguide.